Hi everybody. Today we'll discuss about a few more topics in tensors as it is used in special relativity and their use in special relativity. We have been just talking about them and some examples but not have seen much of their use or considered special relativity in terms of them. So let's start with our discussion which we have discussed before. So let's go back to the tensor of form. So this is a second rank tensor. As you see, I write 2 in the bottom place. And to remind you, this is a type of tensor. It takes two vectors as input and give a scalar as output. In general, it will take two vectors, so A and B. So T is the tensor and give out a scalar. And remember, if I choose these vectors to be the unit vectors, the alpha-ith and the beta-ith unit vector, this gives us the alpha beta component of the tensor. Now, the components are written usually with the same symbol as the tensor itself. I will just not put that bar sign on the top. The question we'll ask though is the following: can we write the tensor T in terms of its components in the following way? So T alpha beta and then some basis tensor alpha beta. Sorry, some basis 1 form. Rather, I'll call it tensor because it's really not a one form, so it has two components. Okay, so can I write this? So let us keep a question mark here. Now, once I have written the tensor in terms of its basis tensor and the components, what I can do is I can try to figure out what the components will be like in this form by the following method. So T, if I put in say the mu and the nuth basis vectors in it, then this by definition is alpha beta and then omega alpha beta, which is the basis tensor, and it has two indices, and then I will get now this necessarily from this relation has to be T mu nu, which essentially tells you that omega alpha beta taking the unit bases in it is nothing but the two delta functions, two Dirac deltas, beta nu. And that I can write as okay, so it is this. Now this I can also write as, if you remember, alpha mu and omega beta nu. And we call this an outer product of these two. So the basis vector of higher ranks can be prepared using the basis vectors of the lower rank. That is the what we have learned here. So let me write that down. Basis, not tensors, not vectors. Okay. Basically, I can write this as here. When I write, this will give me just the components. Usually you don't put in the outer product sign. You put the outer product sign when you write the one forms. So nice. So that is something now we have learned. And so one more thing about this second rank tensor, which is true for many higher ranks also, but easy to see here, is the symmetry and anti-symmetric tensors. See, it is not necessary that you will always get the same scalar if you switch the order of the operations. For example, if I have T as the tensor and I put A in the first place and B in the second place, it is not necessary that it will be same as if I put B in the first place and A in the second place. This is true in general. We call T to be symmetric when this is true, which is TAB is equals TBA. You see, what happens when TAB equals TBA is that if I put in now the unit, the basis vectors here, then it doesn't matter which order I put them in. The right hand side expression gives me the beta alpha component of T, and the left hand side expression gives me the alpha beta component of this T. So if the tensors are symmetric, the tensor components are symmetric in their indices. That is very nice. And this actually carry overs to higher dimension, but we'll come back to that later. Now, if I have any such tensor, I can always construct a symmetric and an anti-symmetric tensor from any tensor. So I can get a symmetric and anti-symmetric part of a tensor in the following way. So I get any tensor. Now I need to remember which place is being operated when. So let us keep the placeholders here. I add to it not there is no C, obviously. I add to it this part, and because I have added, I have to subtract. So I put this again, and then subtract it. This entire thing is twice the tensor T, so I can write the tensor T as half of this. BA is taken positive once and then subtracted out, so there is no harm. If I look at the first part, which we may call the symmetric part of this tensor, I'm sorry, this is the tensor T, and you add it with the opposite thing. You see, if I just stop here for a while, this part I can call the symmetric part, because if I change the order A and B, nothing will happen to this part, because one time this will come first, one time that will come first. So this is the symmetric part of the tensor T. And similarly, you can write down the other part minus now TBA. And this is always anti-symmetric. It basically is the case where this, if I write as T anti-symmetric, if I change the order of A and B, it will pick up a negative sign. So this way I can write any tensor T in terms of its symmetric and antisymmetric parts. Sometimes there is a even shorthand notation followed for this, or when you write the components of this. So you see that all the thing that we have written down, if I instead of A and B have put in some unit vectors, would have given components. So it is written the following way, that T alpha beta equals T alpha beta, and for the symmetric part one uses a square bracket, a parenthesis, and for the antisymmetric part one uses a square bracket, which, let me still tell you explicitly once, is that this essentially means that here I have to do T alpha beta plus T beta alpha to get the component, and here I have to do T alpha beta minus T beta alpha. Okay, so this way, for any second rank tensor, I can write it symmetric and antisymmetric components. Okay, alright, so that's up to second rank tensor. Now we will have to deal with a completely new type of object, which is quite similar. Operations of it is quite similar, but the object is new. So that is tensors of type. Now this has only something upstairs and zero downstairs. So what are these? Remember that the tensors of 0 n maps n vectors to a scalar. These maps m1 forms to a scalar. And the linearity property is still there. I'm not writing or let us still write it down that operation is linear in its arguments. Okay, so what are the examples of this? Well, the obvious example is that of a vector. The vector is m equals to 1. So 1, 0. So like A. That is how we wrote a vector. And the operation, so what it is we'll do is, now we'll just write the opposite way we wrote for the one form operations. It will take a one form in it and it will give me a scalar. How do I get the components? So this is the operation or mapping. How do I get the components? So what we are doing here is exactly opposite to what we did for the one forms. So here I have to put in the basis one forms. So this will give me A alpha. Second rank case, I can have 2, 0. Just from the previous example, this basis will be can be composed of the basis of the vectors. And if we come to more solid examples of this, is the tensor G, which if I put in these will give me G alpha beta. And this G behaves like the metric, but now it has a form 2, 0 instead of 0, 2. So this G maps a one form to a vector. Remember that the G which comes with 0, 2 was mapping a vector to a one form. This is just doing the inverse mapping. And I leave it for you to figure out that in component wise this will look like the following. And I also leave it for you to figure out that G alpha beta, G beta eta is delta alpha eta. These two are inverse of one another. So let me label these as 1 and 2. So your homework is how 1 and 2 comes about. I have not proven it for you. but that is what you have to figure out. We can define the norms of one forms, and they have, so let's say versus norms of a vector. Okay, so let's say I have a vector A and the corresponding one form A tilde. So they are dual to each other in the sense we have discussed earlier. Okay, the norm of the vector A is defined this way, which if I write in terms of the components of these components of vector A, it is this. Then what I can do is I can write this also as A alpha, A alpha. A alpha I can use this expression now to write A alpha as G alpha beta A beta. So this becomes G alpha beta A alpha A beta. This is nothing but A tilde mod square. So you see that the norm of the one form and the norm of the dual of the one form, which is the norm of the corresponding vector, are exactly the same thing. So the norms are same. Norms are sometimes written with square or sometimes written without the square. Sometimes it is written as A mod or sometimes written A mod square, but doesn't matter. If A mod matches, A mod square will also match. Let's now generalize everything and we say that tensors of you can have M upstairs and N downstairs. So what does it do? It converts M one forms and N vectors to scalars. So let us consider an example. So let's go with the tensor of say 3, 2, which means that this is my tensor. It has 2 slots for a vector and 3 slots for one forms. So let's say the one forms are P, Q, and R. So these are the 3 slots, and the 2 slots for vectors are A and B. How do I write it in terms of its components? Well, you see that the one form components will be downstairs. So let's call them alpha, beta, gamma. And vector components will be upstairs. And then I write the one form basis first. and then the two basis vectors. Okay, so that is the whole complicated way of writing the tensor. What happens? So let's take another example. So everything that we have learned for the upper and the lower indices apply here. So let me give you some old notation for the upper and lower indices. These are called contravariant and these are called the covariant indices. Okay, so which will contravariant will corresponds to these here, covariant will corresponds to these here. This is the usual way people used to call it, and sometimes this notation becomes much easier to use in many examples, so we will use that notation also. There's no harm in learning more things than less things. So now, so let's say that how do I get the component? So that is, let's once write down that I put in the basis one forms in the place of the one forms, and I put in the, so that they're separated by a comma. The left hand side is for the one forms, the right hand side is for the vectors. So this will give me the T alpha, beta, gamma, mu nu component. What if I not use one of them? So say I so put in P here, Q here, and don't put in anything, and then I have A and B. What will this be? Well, this will become a vector which is type 1, 0. So another example, say G alpha beta, T alpha beta gamma, mu nu. Okay, this I can write as, so let's keep G alpha beta gamma mu nu here. This I can write as G alpha eta and then a delta with eta beta. Right, so delta function will change this eta index in the G alpha eta to beta, which is what I have in the left hand side. Why do I do that? So G alpha eta times T alpha beta eta will change alpha to eta in T. So let's do that. So T will become first index comes down. Now this I still call T, but remember that it has different slots. It has 3 slots in the downstairs and 2 slots in the upstairs. And then I have the G is used up, right? And in the next line, you can see what you can do. Because this is a delta function, the sole purpose of that is to replace eta with beta. So this becomes T beta, beta gamma, mu nu. Okay, so there are a lot of other combinatorics you can do, and let me remind you that this becomes a tensor. What type of tensor is it? So that's you can think of as a homework. There are some homework problems I have given on this combinatorics. Okay, so one more topic, which is something that we'll have to change the definition later, but will be our starting point in going to general relativity at some point. So we consider derivative of a tensor, and just as an example, we choose the tensor to be 1, 1, and the derivative is by a scalar. Okay, so let's see what it will be. So the tensor is 1, 1, so this tensor I can write as if I take the derivative, that is dt d say tau, what happens? Well, the one form and the vector bases are not their constant values 1, 0, 0, 0 in the type of coordinate system we are dealing with in special relativity. So they will just remain as it is. What I will get is dt d tau as the basis remains as it is, because they doesn't change with tau. However, this I can do a trick, so I can consider this derivative with respect to some gamma, and then I get a dx gamma d tau here, which is nothing but u gamma. It's interesting thing to notice here is that this becomes a derivative along a curve defined by u gamma, which is what we were talking about earlier. So we call such things as gradient of t. I mean, you can debate whether should we call it the word gradient, but that is how I'm writing it with that inverted triangle sign. And with our definition of, or with our notation of the derivative with respect to x gamma, we can write it in this following way. So if I, for example, if I have a derivative of one form, so say p, that will be p alpha comma gamma u gamma, and then w alpha. So that is what a derivative of one form is. Now, this is all that we will need for special relativity in terms of tensor analysis. So now in the rest of the discussion today, what we will do is we will try to use this in special relativity. So let's go ahead and try to do that. So dynamics of a particle in special relativity. Okay. Now remember that we are dealing with inertial reference frames only, because that's why we are in special relativity. If we could have done in any reference systems, we would have done with general relativity. Okay. So now, how do we find out the dynamics of things in special relativity? So there are two ways we know. One is Hamilton's principle. What does Hamilton's principle tells you? That action is an extremum between the fixed points in the trajectory. Between the fixed point in the trajectory for the correct trajectory, or for the trajectory, say. This is Hamilton's principle. And we have, alternatively, we have Newton's laws of motion. Which I am not writing down because I guess that is you are very familiar with. Okay. So Newton's laws of motion, the first law tells you, it actually defines the inertial reference frame, but it also tells you free particle moves in straight lines. Now let us try to use these to first see the trajectory of a free particle. How to find out the equation of motion or the trajectory of a free particle. Okay. How do I go about it? The first thing I notice is that I should write down an action that is Lagrange invariant. That is a Lagrange scalar. Why do I do so? Because then the same action can work in any reference system. It will tell me the trajectory in any reference system. Okay. So first we say that we will write down the action in Lagrange invariant fashion. Trajectory is, remember, this is something we have done before. So trajectory is parametrized. This is except if you are talking about the trajectory of light, where the proper time is always 0, but otherwise the trajectory is parameterized by the proper time. So what do I mean by that? So I have the x positions which are given by x as a function of tau, where tau is the tau is the proper time along the trajectory of the particle. Or you can think of that there is an observer moving with the particle. Tau is the time elapsed in his clock. Okay. Now it looks like that there may be a relation between the proper time and the action, because proper time is something that changes with the trajectory, it levels the trajectory, the action is also supposed to level the trajectory. The action is Lagrange invariant. The proper time is Lagrange invariant. But let us ask the question that how do we calculate proper time from any reference frame? How to calculate tau from any reference frame? So what we are talking about? We are talking about that a particle is moving in a trajectory. And let me draw the trajectory of the whirl line of the particle in a 1 plus 1 dimensional type of diagram where I have only one spatial axis because that is the best I can do in this board. So say this is my trajectory. Okay. And at a given point, so this trajectory starts at certain proper time and its end at certain proper time. And as you can see, the particle may be accelerating or decelerating in this reference frame. Not necessary that it has to have a constant velocity. Now, any point in this trajectory, as we are saying, is leveled by the proper time. So, if I ask the question, infinitesimal distance, space-time distance, how much is that in this trajectory? That you will tell me that by this, I know that ds square is g alpha beta dx alpha dx beta. You also remember in the reference frame of the particle, this is essentially c square d tau square. Which means d tau is nothing, or c d tau, let me write with the c easier, is root over of g alpha beta dx alpha dx beta. If I just for a moment break it out in terms of the components, so this is c square dt square minus, let's write this as dx square plus dy square plus dz square by c square dt square. Obviously, I cannot do that for free, so this is c square dt square here as well, which essentially tells me that c d tau is nothing but c dt, which I can take outside, times 1 minus v square by c square. This v is the 3 velocity or magnitude of the 3 velocity, which does depend on time because as you can see, this particle can have an acceleration. An accelerated particle, obviously the velocity changes with time. And now I can do this integral actually to get the proper time. So I can calculate the time elapsed between initial and final, proper time elapsed, as integral of t initial to t final dt of this entire thing. So you realize that there is a way of calculating the proper time that is spent along the trajectory of an arbitrarily moving particle. Okay, all that you need to know is the velocity of the particle at all time. How do I use it? Well, to use it, let us come to a game. So this is, let me keep it here. That's how to calculate proper time elapsed along a trajectory from any reference frame. So that is important. Okay, so once we know that, we have enormous power, as you will see. So let's play a game. The game is that I have this my space axis, only one space is allowed to be drawn. So this is my time axis, x1 and x0. And I have two events, so let me denote x0 here. This is a line which is parallel to the time axis. And I have two events, one is here, the other is here. Let's call these events A and B. Okay. So basically, they're at the same point but at different times. What you have done is, you have asked several people observers, each observers must have a clock, to go from A event to B event by their chosen path. Okay. The person with extreme value extreme tau spent wins. The person who has spent the extreme value of tau AV will win. Okay, so the person who has the extreme proper time elapsed, that extreme can be maximum or minimum, will win. Okay, so what can be the trajectory? So they say this or this or that. There can be many, even there can be one which is just going that way. Okay, so that is the trajectory of a person who doesn't move. He stays there all the time, so he will eventually be there. We know how to calculate the proper time of all of these particles, all of these observers. The proper time spent by each observer will be given by TA to TB. This T is calculated in any reference frame, and then dt root over 1 minus v square by c square. Now see, do you see who will have the extreme value of tau? For everybody who has certain velocity, anybody who has certain velocity, anybody having Vt not equals to 0 at any t will have, see, if that is true, then this term will take away something from 1 less proper time spent than just TB minus TA, right? What is the proper time spent? Which observer spent the proper time TB minus TA? Well, this observer who just sit there, does nothing, the laziest one. Laziest observer tau AB equals TB minus TA. Everybody else has a lower time. So this observer has the highest time, highest proper time, the blue observer, and he wins. But that is also the observer who was at rest. To start with, all the observers were at rest. And if I believe in Newton's second law, they were supposed to be at rest all the time. Because there is no force on this particle, you are talking about a free particle. So what do you see here? You see tau does serve as a proxy for the action which remains extremum along the trajectory. So with this knowledge, we along the true trajectory, because the true trajectory we already know is the trajectory where the particle doesn't move. That's Newton's second law tells us that. So this let us find out the Lagrangian for a free particle. In special relativity. How do I find that out? Well, I now know that my action is given by this integral, where I can write this, or I can be a little more clever and write this, which is in a covariant form now. And it turns out you need certain constants before that. So let me put those constants properly such that you get the right Lagrangian. The story is a little longer. How do you get the constants right, etc. if you ask, but we will not go in there. But one can figure it out comparing with what you already know. So this is minus MC d tau, which one can write as, take one C inside, then this becomes G alpha beta dx alpha dx beta. This is what we wrote earlier. What I do, one more clever trick, I divide both of this by tau, and then I get a tau here, which let me write this in the following way: integral of minus mc root over of g alpha beta dx alpha d beta is nothing but the four velocities u alpha u beta and then d tau. So this is the action, and the action we know, if I want to write it in terms of the Lagrangian, it is of the form L dt. Here what we have done is we have find out an action, find out a L, which will be this entire thing, which is Lagrange invariant. You see, this L itself is Lagrange invariant. There's no hanging indices. G alpha beta U alpha U beta is the dot product of U alpha U beta, which is a scalar. M is the mass of the particle, which defines the particle is a scalar. C is obviously a scalar. That's second postulate of special relativity. So this is L. Let me write it even more explicitly, that the action is L x alpha U beta and tau. So it can be function of these quantities, and we understand what is our Lagrangian for a free particle. Once you know the Lagrangian, so let us try to write down the Euler-Lagrange equation. The Euler-Lagrange equation will be, in this case, dd tau del L del velocity, which is u, say u alpha, minus del L del x alpha equals 0. Now you see that this case the Lagrangian is not a function of x alpha, which is better not be. Otherwise, if it is a function of x alpha, then where you do the experiment will determine the property of the free particle, which is not supposed to be. So the second term del L del x alpha is anyway 0. So let us find out the canonical momentum, and you immediately realize that canonical momentum, which is defined by del L del u alpha, must be component of one form. The canonical momentum is a one form. So this is this, which if I now work out, so let us work this out. So this is mc del u alpha of this entire thing. I'm just doing the derivative here, but I will tell you what I am doing whenever it is required. So when I take the derivative with u alpha, so this u alpha goes, so I get g alpha beta u beta. When I take the derivative, keeping this constant, take the derivative with respect to that derivative will give me a delta beta alpha. So I will get again and I had a half because this thing, entire thing to the power half was there. So what is this? First of all, you realize that the denominator is nothing but c. U alpha u beta is g alpha beta is c square, root over of that is c. So I have only minus m left over here, and in the numerator I have two of these things because g beta alpha is same as g alpha beta. G is symmetric, so I get g alpha beta u beta, which is nothing but u alpha. So that is my canonical momentum. It's a one form. You can construct the corresponding components of the vector. And Euler-Lagrange equation. So what happens to the Euler-Lagrange equation? So that let us write it down here itself. It is very straightforward. You see that I have to take a derivative with respect to tau of p alpha, which will tell me that w alpha equals 0. W alpha is nothing but the dual one form to the 4 acceleration vector. I guess you are familiar with these languages now. Okay, so that's the case for a free particle. But what about if the particle is moving in a vector field? Particle in a vector field. And when I say vector, it's a 4 vector field. See, in this case, it is not very difficult to see that the first term that we had will remain as it is, because otherwise when you switch off the vector field, you will not get back the free particle case. So this will remain as it is. The vector field has a corresponding dual is, say, A alpha. Then how do I write? The question is, how do I write the effect of the vector field? Well, this particular vector field, say, comes with a U alpha here. A alpha can be a function of the coordinates. Okay, so this is the case. This essentially is the Lagrangian for a particle moving in an electromagnetic field. The A alpha is the 4 vector or the components of the A alpha upstairs are the components of the 4 vectors, 4 potentials. Sorry. Let me not go through the calculation, but if you do this, what you will get now is m omega alpha equals, I will have a E here, which is the charge of the electron, U beta, and then A alpha beta minus A beta alpha. Which we write as a tensor. This tensor is the form, this form, I'm sorry, this tensor is of this form, obviously, because the indices are downstairs. This we call okay. So that is something that you have learned in electrodynamics course. So I will not go through the calculation, but please derive. So your homework. So derive the Euler Lagrange equation. This one. So this is your homework. Now I'll give you another exercise. This is not what you have seen in special relativity, because special relativity just doesn't work this way. But what if I had a Lagrangian, which is obviously the first term will be always there. But then I have something like mu times phi. Phi is a scalar which depends on x alpha, x and u both. Okay. So this is a very typical type of Lagrangian. So just figure out what is the Euler-Lagrange equation for this Lagrangian. So we'll end our discussion today. So what we have done is we have paved the language of tensors and have seen at the end how you use them in special relativity. And remember that this, by definition, looks like an anti-symmetric tensor. And that is what the electromagnetic field tensor is, an anti-symmetric tensor. It has certain properties, but we will not go into those in detail. Thank you.